Okay, so the bad news today is that I'm going to talk about stacks, and the very bad news is that I'm going to talk about higher stacks, actually. So that's the goal of my first lecture, is to present a formalism for higher stacks. And this formalism actually existed since maybe 20 years already, and that's the theory of simple sheaves. That was, I think, originally from Illusi and Joyal, and then many other authors.
Maybe you can write larger.
Oh, okay.
And press a little bit more.
Okay. So the bad news is this one, and the very bad news is this one. Okay, also I should say that the stacks I will talk about will have probably a very different flavor than the stacks we have heard about in the previous lectures. There will be more, so that these stacks will be more coefficients for cohomology. And in particular, I won't look at them as geometrical objects. So they will not be like algebraic or topological, or I don't know. So these are just stacks without any algebraic or topological structures. Okay, and the plan for the talk today, I hope I will have time to do everything. I will start with sheaves. This will be a review of the construction of the category of sheaves, which is not really classical constructions, but it will explain how one can construct the category of stacks. So then I will go to stacks. Then I will compare sheaves and stacks. I will also compare the previous definition of stacks with this new definition. So about the terminology, I will use one stack to denote the definition we have heard about already. This is stacks. And in the last paragraph, I will talk about enriched structures. And finally, non-abelian cohomology. Okay, everything I will say today is actually valid over any Grothendieck site, but for some reason I will work over the big site of topological spaces, just to stay in the same context. So T will be top big site of topological spaces. Okay. So let me start with sheaves. So one can start with the category of pre-sheaves on T. These are just contravariant functors from topological spaces to sets. and the morphisms here are just natural transformations. And I consider a subset of morphism in this category I call W. So this is the set of morphisms, of presheaves, such that for any space and for any point in the space, the morphism induced on the fiber is an isomorphism. On the fiber. And as E and E prime are only presheaves, it doesn't imply that F is an isomorphism. So this is, in other way, W is the set of local isomorphisms. Well, you can restrict the presheaf to the topological space just by looking at open subset. This gives you a presheaf on the topological space. Just a usual fiber, take an inductive limit of neighborhood of other points. So it's just the fiber of the restriction on the small side. Okay, and to such a data, so we have a category of presheafs and a subset of morphism. There is a very general construction which consists of inverting formally the morphisms in W. So I'll explain what it is. It's a category denoted by W minus 1 presheaf together with a functor such that the functor L sends any morphism in W to isomorphisms here. This is contained in isomorphisms. This. And the second condition is that this data is actually universal. So L is universal means up to something, like I think Angelo told us what it is. Universal for this kind of data. So that means, well, roughly speaking, it means that if you have any other functor from the category of presheafs to any category which sends W to isomorphisms in the category here, then there is a unique, well, essentially unique factorization here. And it's a general fact that such a category exists. It always exists. So. And now the remark of this first paragraph is that this category is actually naturally equivalent to the category of sheaves on the big side. So there is the subcategory of sheaves on topological spaces of big sheaves And one can compose with this functor. So this induces an equivalence between sheaves and this abstractly defined category. So there is a conclusion to this proposition, which is quite striking in a way. It's that the construction of this category only depends on the category of presheaves and on the subset of local isomorphisms. There are no descent condition anywhere, no sheaf condition. So that means that the category of sheaves can be constructed without even defining what a sheaf is. So one doesn't need to know what a sheaf is in order to define the category of sheaves. Well, it's a strange principle, but it's like this. And that's exactly what I'm going to do with stacks, because what is really a stack, it's a higher stack, I mean, like an infinite stack, is really a tricky question. And I think people doesn't agree. There are many definitions, and everybody has his own descent condition, and maybe they're not the same. But using this principle, it's really easy to actually define what are local equivalences. Everybody agrees with what are local equivalents. So then there is a reasonable construction of the category of stacks without even defining what a stack is. So that's the principle of this talk. We're going to make the same construction for higher stacks. Okay, that will be the part 2, and then 3, 4, 5. I hope that I will convince you that this category of stacks is actually an interesting category. Yeah, so. W is this set here. So it's a subset of morphism in the category of presheaves. You take all morphisms of presheaves which induces isomorphism on the fibers.
Yeah, so what's W inverse times this?
Oh, you mean, no, I'm not going to explain how to construct this category. I just say that it exists. There is a natural construction. It's like the localization of a ring, if you want. There is a universal thing like this. I'm not going to explain how to construct it. Okay. So now I don't start with presheaves of sets, but I will start with presheaf of simple sets. And so that will be presheaves so that means contravariant functor from T to simple sets. And if you don't like simple sets, that's possible. One can replace everywhere in the talk simple sets by topological spaces. So the theory of simple sets up to equivalences is equivalent to the theory of topological spaces. So just think, if you don't know what a simple set, just think that it's a topological space. But then there is I should warn you that there are topological spaces here, and they will play a very different role in the talk. here you should think of manifolds. So that's really the topological spaces we want to study. And here you should think of homotopy types. That means that they are only defined up to equivalences. You can make retraction homotopies and things like this. So up to equivalences. So these are the coefficients, and these are the geometrical objects. So, okay, then I start with that. So they are just presheaves. So it's just a rule which, for any, maybe I can make it more precise. It's just a rule which takes a topological space and map it to a simple set of section, and then for any continuous map of topological spaces, one has the restriction, which is a morphism of simple set or a continuous map of topological spaces if you work with topological spaces, and such that the composition composes well, and so on. So this is just this category. Now I define a subset W of morphism, which will be very close to this one. I take the set, I call F, you see, of all morphisms in this category, such that for any space and for any point in the space, there is a morphism induced on the fiber. The fiber is then a simple set. It's just, if you take the fiber of a presheaf of topological spaces, you have a natural topology on it. So there is an induced map on the fiber, and you ask that this map is a weak equivalence. So let me recall what it means. It means that it induces an isomorphism on all homotopy groups. Yeah, that's what I was. Yeah. Yeah. It's the fiber of the restricted sheaf on the small side. Yeah. Yeah. So a weak equivalence is a morphism which induces isomorphism on all homotopy groups. So it means that on pi knots they have the same connected components, and then homotopy groups with value in any base point. So I don't write a base point.
Homotopy groups, the limits of the homotopy groups of the
yes. Yes. So these are actually the fiber of the homotopy presheaves, if you want. Well, there is a problem with base points, but anyway.
Right. On the general Grothendieck side.
Yeah. So when you want to define what is on the general Grothendieck side, you define homotopy sheaves, and then you say that you have an isomorphism of homotopy sheaves. Well, you sheafify the homotopy presheaves, and then you say isomorphism. Okay. But it's more easy. It's just the fiber. Okay. So these are the sets in W, and by definition, what I call the homotopy category of stacks is W minus 1 of and the notation is HO of t. So these are pre-sheaves of simple sets where you invert formally all the local weak equivalences. For this, I should have said that are the local weak equivalences.
So the objects are pre-sheaves,
Yes.
and I suppose that two pre-sheaves are isomorphic if and only associated sheaves.
Yes. It can be described, I mean, the objects are pre-sheaves, and morphisms between two pre-sheaves, you just take the set of morphism between the associated sheaves, and that describes the category. But in general, the construction is very complicated. It's a fact that one can describe it like this. So it's the same here. The objects actually of this category are really simple pre-sheaves without any condition. But then, if there is a morphism like this, then it induces an isomorphism in this category.
The arrows in terms of transition can be described by some steps, or you need...
No, you need an infinite number of steps. Well, there is a description by 2 steps, but then you need a model structure and fibrantly conditions, and I don't want to go into that thing. Yeah, there is, yeah. Yes. Yeah, that's true. Yeah. Yeah. So that's actually that's the way one can describe this thing by actual stacks, I mean simple pre-sheaves with descents with respect to hypercovers, but I'm not going to use that. So. Okay, so let me go to sheaves versus stacks. This is just a very simple observation that the category of stacks actually contains the category of sheaves. So yeah, I said the homotopy category of stacks, and I will say the category of stacks. By this I mean the homotopy category of stacks.
So this is different category than what we consider in last lecture.
Yeah, I will explain the relation with the one with the previous lectures. I say the homotopy category because there is a fancy homotopy category which is an infinite category, and I don't want to talk about higher categories. So I will say category of stacks to say this thing, HO of t. Yeah, there exists a full embedding. I don't know how to write this thing. Sheaves into stack, and its image consists of objects such that the fibers are acyclic, meaning that they don't have homotopy groups except maybe a pi naught. So the terminology is zero truncated, and that means that pi I of fx is 0 for any I greater than 0, and again for any space and any point in the space. So all the fibers are acyclic spaces. They are just, it means it's a space which retracts to a set, to a discrete space. So if you prefer, Fx is homotopically discrete. So, okay. And there is a very easy construction of this functor. Let me describe it. You take a sheaf, you just see that as a presheaf, and now for any space, the set of section over this space is just a set, and you see this set as a discrete symmetrical set. Or a discrete topological space, if you prefer. And then, of course, the transition morphisms between discrete symmetrical sets are always morphism of symmetrical sets, or always continuous morphisms. So it actually defines an object here. So what I just say here is that the category of presheafs is actually a full subcategory of the category of symmetrical presheafs. But just by requiring that each value is a discrete symmetrical presheaf. And then one can just project to the homotopy category. So there is this localization functor. I don't know if it is so easy to, I think it's not very difficult to construct, to prove that it is a full embedding. There is actually a functor in the other way, which is an adjoint, and one check that when one do that, it's isomorphic to the identity. It's a kind of exercise to prove this proposition. Okay, so that was just a remark that the category of stacks contain as a full subcategory the category of sheaves, and there is an explicit description there, just stockwise acyclic symmetrical presheaves. So this part is more interesting. It will say that this category of stacks actually contains also the category of one stacks, I mean the category of stacks defined by fibered categories that we have seen in the previous lectures. There is a small subtlety that this is just a category, and I think somebody said that one stacks form a two category. And a two category cannot really embed in a one category. So there will be some truncation. I mean, I will work with the category of stacks by forgetting two morphisms. So that's what I'm going to explain here. So we have seen that there is a category, I will denote it like this, which is the category of stacks in groupoids on T, defined in the previous lecture. So the objects are.
Then you see you mod out by two isomorphisms.
Yeah, I will go into mod out by two isomorphisms. So the objects are fibered categories with descent, with the stack condition. And the morphisms, so there are one morphisms, which are natural transformation, functors which commute with the projection. And there are two morphisms, I think somebody draw a picture like this. So these are fiber categories. These are functors which commute with the projection. And this is a natural transformation between the two functors, which also is compatible with the two projections. And these together form a two category. One doesn't really need to know what is a two category, but this induces equivalence relation on the set of one morphisms. So if you have F and G, two one morphisms, and such a natural transformation, then one says that F is homotopic to G, meaning that there exists such a thing. We don't need to specify it. Okay, so what I will be interested in is something I call HO of one stack. And it's a category where you have the same objects. So the objects are the same. So they are just stacks in groupoids. And the morphisms between X and X prime are homotopy classes of morphisms. Okay, so this is just an analog of the, when you construct the homotopy category of spaces in topology, you do exactly this thing. So that's exactly the same. Okay, and that's the homotopy category of one stack, say, by definition. Say one stack in groupoids. Okay, so the result is that this category actually embeds in the category of stacks. And there is also a characterization of the image in the same way than here. The image is not the zero truncated simple shifts, but they are the one truncated simple shifts. And the image consists of one truncated F So this means that by I of f of x is 0 for I greater than 1 for all spaces and all points. So all the fibers are one truncated. So there are nothing else than essentially points and paths between the points. No relations, but no two spheres, for example. Okay, and the construction which associates from a one stack in this sense is not very difficult to explicit. Actually, I will explain how to do that. But it uses something which is quite unnatural, is that I think people have explained that a fibered category in groupoids is not really a presheaf of groupoids. There were these groupoid fibers. I mean, that's the fiber over a space X, and there were pullback morphisms. But the pullback morphisms were not really strictly associative. There are this thing that is not equal to this, but only isomorphic. But anyway, there is a way, which is actually an easy way, to make this thing into an actual presheaf of groupoids. So even if fibered categories are not really presheaf of groupoids, there is a natural way to make them into presheaf of groupoids. And that's why taking actual presheaf of simplicial sets is enough to construct the category of stacks. One doesn't need something like a weak presheaf of simplicial sets. This is not needed. So okay, this is the construction. Start with fibered category in groupoid, and you define a presheaf of groupoid. So that's a strict presheaf, really, by the following formula. The value at a topological space X is nothing else than the category of functors over T from the fibered category associated to the sheaf represented by X. So any topological space corresponds to any topological space. There is this X underline, which is a fibered category in sets, which represents the sheaf represented by X, actually, to X. And these are just so functors from X to T, which commutes with the projection, X to X, which commutes to the projections to T, and natural transformation, which also commutes with the projection to T. So this is the category of functors from this fibered category to this fibered category. And as it's not difficult to check that X goes to X underline is actual, it's a strict functor, then this is really a strict functor in X. I will put strict presheaf groupoids. And that's this has a name. This is the strictification principle. Strictification. And this construction is due to Grothendieck, actually. And this is a principle which is known from topology since a long time, that weak presheaves can always be strictified. Like, for example, weak presheaves in simplicial sets. There is a notion of weak presheaves of simplicial sets, which is quite nasty, but they can all be strictified. And the strictification is natural in the sense that it gives, it's functorial in X. So it really gives a functor from one stack over T to a presheaf of groupoids. And it's even more that this functor is actually an equivalence of two categories. It is an equivalence of, well, let's say two categories. So this is Sorry? Yes. So groupoids form a two category because groupoids are just fiber groupoids over the points. So this is the category of stacks over a point. So this is a two category. And preshift with value in a two category is again a two category. You just take functorial natural transformations. Okay, so that's a very nice principle that, and there is a functor in the other way. I mean, everything is very explicit. It's not an abstract theorem which says that one can pass to. There is really, you know, this construction is really very explicit. Okay. Sorry? Oh, I put stack. Yeah, I should put pre-stacks. You're right. Thank you. Yeah. This is actually, it has nothing to do with descent, what I say here. It's just purely functorial, excuse me. So this is the fibered category without any descent condition. Then it induces an equivalence of two categories. Then there is a descent condition here. There is also a descent condition here, which is descent for hypercover. So like covering here is enough. And the equivalence passed to the equivalence of object with descent. But this is not, yeah, I don't want to talk about that. It has nothing to do with the topology here. Okay, so now I have this presheaf of groupoids, and I just want to recall that a groupoid G, well, it's a generalization of a group, and you probably know that a group has a classifying space. And a groupoid also has a classifying space. Called PG. And it's characterized up to equivalence. It's characterized by the fact that it is one truncated. So it doesn't have any other homotopy groups than pi naught and pi 1. And that the fundamental groupoid of this space is equivalent to the groupoid we started with. So the fundamental groupoid is it's a groupoid, so it's a category where objects are points of the space and morphisms are homotopy classes of maps between the points. So it's a generalization of the fundamental group where you don't fix a base point, you take all the points at the same time. It's not really a... So that's the classifying space. I mean, if you take G to be a group, then it's just a connected one truncated space such that pi 1 is G. That's the classifying space. And there is a functorial construction starting from a groupoid to a classifying space. Here I say classifying space, but there is also a simplicial model of that. So there is a simplicial set, which is a classifying space. This is not a problem. So what we can do is take B of this presheaf of groupoids. So it goes from topological spaces to groupoids, and then by B, it goes to simplicial sets, or topological spaces if you prefer. And this lives in the category of simplicial presheafs. And one can just compose with the natural projection to the homotopy category of stacks. So it seems a little bit complicated, but actually in practice it works very well. So it's just a matter of being used to pass from categories to spaces. It's just this duality. So when you make this construction, it gives a functor from one stack, so over T, to the homotopy category of stacks, maps X to B of Fx. And it's not difficult to show that if you have two morphisms which are homotopic here, they go to the same morphism here. So there is a factorization. Here. And this is the functor of the proposition. And again, it's not, well, there is a lot of details to check, but it's not very difficult to show that this is a full embedding and that the images exactly correspond to what I said. So this is, okay, so in conclusion, this thing contains sheaves, and it also contains one stacks, well, at least up to two morphisms. Okay, so a small remark before going to part 5. These two propositions, so sheaves are 0 stacks if you want. Then there is this thing about 1 stacks, which correspond to one truncated object. This can be generalized to higher stacks. Well, I don't know any references for a definition of an n stack besides n equal to 2. I think Larry Breen gave a definition. But you can trust me that there exists one of an n stack in groupoid over T as a certain fibered category, well, fibered n category. So there is a formalism of n categories. There are several definitions actually, and one can just choose the one you like the most and go. But it's not really clear what is the fibered condition, but I think some people know how to do that. And the proposition actually generalizes to a general theorem that there exists full embedding. So here I put n stacks over T. N stacks will be a n plus 1 category, and I play the same game. I just neglect everything up to 2 morphisms, and it embeds in this thing. And the image consists exactly of n truncated objects. Okay, so this was just a remark to say actually that this really contains up to a good definition a category of higher stacks. And I'm sure that this is also valid for n equal to infinity. And then there is I think there is a real problem to define this, but anyway, probably people will come up with a definition. So there will be an infinite category of infinite stacks in groupoids, and then the full embedding will actually be an equivalent because an infinite truncated object is just any object. So morally, this is really the homotopy category of infinite stacks. So that's what I wanted to say. So n equal infinity would imply, so whatever this means, would imply that HO is the category of infinite stack. And that it's quite amazing that the category of simple presheaves, I mean, this category of simple presheaf has existed since 30 years and maybe more. And it's only well, not maybe very, but only recently that people started to see that they correspond to infinite stacks. And I think the first who really used the word stacks for this thing were Carlos Simpson. So I think this is I mean, most of his work about higher non-abelian Hodge theory use this point of view on higher stacks. Okay, so now I have said that, well, I hope you are more or less convinced that this category is interesting. I will now explain that it's not really good for certain things. So these are concerned with enriched structure. The problem here is this HO. Sometimes it's not a really good idea to neglect two isomorphisms. And there are some abstract situations where two morphisms are really needed. And the first situation is, for example, to define fiber product of stacks. So I remind you that for diagram of one stacks, so stacks in groupoid, there is such a fiber product, and it has a universal property. It's a universal property. It's a two universal property, but it's really a universal property. And but this universal property is in the two category of stacks, and the universal property doesn't exist anymore in the homotopy category. And one can see that in the construction, that to construct this thing, you take object here, plus, like this plus a homotopy here, that is going to be lost.
So H0T does not have fiber product?
No. So that's what I wanted to say here. H0T does not have fiber product. And that's a general thing. Usually when you do a construction by localizing, usually there are no fiber product. And it's the same problem with the derived category. It's the same problem with the homotopy category of spaces, the same problem with the homotopy category of spectra, I don't know, any kind of homotopy category in math doesn't have fiber product. So there is a way to try to solve this problem. In the derived category, there is this triangulated structure, which does not solve this thing, but at least allows one to talk about cones of morphisms and triangles, and it looks a little bit like homotopy fiber product. In topology, topologists have invented what I call homotopy limits, and a particular case is a homotopy fiber product. But this homotopy fiber product is really depends on more than this category. It depends of the model category, which is over that. So it depends on the model structure on the category of simple preshifts, and not only on the homotopy category. Okay. So so even if this category does not have fiber product, it has homotopy fiber product. So however, but these homotopy fiber products, once again, are not well defined only here. One needs a little bit more. So it's defined for a diagram in the category before localizing. If one takes a diagram in the homotopy category, then it's not well defined. It's well defined up to a non-canonical isomorphism, and that's really a problem. It's not functorial. Okay, so if you have a diagram as actual preshifts, then there exists something which replaces the fiber product of one stacks. I don't know what's the standard notation, but oh, sorry. I will denote it like this. And it's defined where? It's defined level-wise. You just take level-wise. So for each space, you have a diagram of simple set or of topological spaces, and you take the homotopy fiber product of this. So by definition, it's just f1 of x, 2 of x, 0 of x. And so there are many ways to define this thing. Actually, it doesn't really. Yeah, I'm not specifying the model structure here, but everything I'm saying actually will only depend on equivalences, so it doesn't depend really on the model structure. And also, yeah, I prefer not to talk about model structures. I will just define what. Yeah, well, I mean, yeah, okay, I understand that if you really want to show that this is a homotopy fiber product, you probably need a model structure to prove things. But I'm just stating the results without saying that one needs a model structure to prove them. So that's what I mean.
It puts them in a context where you see the very good universal properties, they satisfy how to construct them.
Yeah, I will talk about that later, and it's not going to involve model structure, but infinite categories. So I really don't want to talk about model categories. Okay, so let me finish this thing. So this is a general construction that when you have a diagram of simple sets or of topological spaces, there is a homotopy fiber product. It can be defined, for example, like this. So this is just the product. This is the product, and this is the space of path on. So this is the morphism from the interval to C. And the two projection maps a path to the first coordinate and to the second coordinate. So, and that's by definition this thing. So a point here is really 2 points, A and B, plus a path between the two images in C. And one needs to specify this path. So one find again this construction here that one needs to specify the isomorphism in Z. That's exactly the path that we specify here. Okay, so that's one possible definition. And you just do that level-wise, and I think this is functorial. If it is not functorial, one should do that functorially. And that's the homotopy fiber product. But, okay, so it has a nice property that there is a long exact sequence.
The idea here is that the space of path is a vibration of the that's the idea.
Sorry?
The space of path is a vibration of C cross C and it's homotopy.
I guess, yeah. Yeah. The idea is that one should replace one of the two maps by a vibration and then take the usual fiber product. It's a derived version of the fiber product, exactly. Okay, so now it's this thing comes with two projections. So there is a what? Yeah. Oh, I don't know. Yeah. There is a commutative diagram like this in the homotopy category. But this is not a fiber product, and again, it doesn't have a universal property in this category that is not Cartesian. So the situation is the following. There is this category HO of T, and to define this homotopy fiber. No, it's not Cartesian in the homotopy category. No, I mean the homotopy fiber product of these things doesn't exist in HO of T, so it cannot be Cartesian.
Are you writing the diagram in here? I mean, there's
Yeah.
a diagram. Well, the image of the diagram.
No. I'm writing the diagram in HO of T.
Well, image of T is in Cartesian.
No, it's not. I can.
It's commutative.
Yeah, it's commutative, but not Cartesian in the sense that there are no fiber products, so it cannot be Cartesian. No. Yeah, so it seems that I'm trying to explain something difficult. So there is this category, and to define this homotopy fiber product, apparently one needs more structure. One needs more than the homotopy category. So one needs this thing. And that's why I call this thing enriched structure, so that they don't come, the homotopy fiber product doesn't come naturally from the homotopy category of stacks. And that's a very bad thing. That's really, really bad. And there are many situations where this causes a lot of problems. There is another problem, which is a generalization of that, is that HO of T does not have limits or colimits. It's the same way, but there is also a notion of homotopy limits and homotopy colimits in the model category, which allows sometimes to make some construction, but still it's not an invariant of the homotopy category. One needs additional structure. Okay, so just remind, I will give another example. Just remind that one needs additional structure on HO of T. It's a kind of non-abelian triangulated structure, if you want. Let me talk about a similar problem. Okay, so this is the first enriched structure, the existence of homotopy fiber product, whatever this means. There is another enriched structure, which is the simplicial Holmes. So there exists a functor that I like to call R-on, because R means that it has to be derived. It goes from the homotopy category of T across the homotopy category of T op and goes to the homotopy category of simple sets. So this object only exist up to a weak equivalences. They are not functorial as simple sets. They are functorial only in the homotopy category. And they satisfy, there is a universal property that satisfy, is that when you look at the homotopy classes of morphism from a simple set A to this space, this is the same as morphism from it's the same as the morphism of stacks between the external product of f by A to f prime. So this is just defined level-wise. You just take each fiber and you cross it with A. So that's the universal property, and it characterizes this thing up to unique isomorphisms here. But the other problem, so the problem here is that our is not functorial. That's only up to weak equivalences. And that's exactly the same kind of problem here, that these homotopy fiber products really doesn't have doesn't have a universal property, or if you start with a diagram in H of T, then the homotopy fiber product is not really functorial and so on.
Sorry, how have you defined the values in the homotopy category of simplical sets?
Yeah.
So in this category it is functorial.
Yeah.
So it's not functorial when you just speak and its value in the category of simplicial.
What I mean is that it doesn't factor like this. So this won't exist. Okay, so this is an additional enriched structure on the category of homotopy, or the homotopy category of stacks, is the existence of such a things.
So take phi 0 that you get the right.
Yeah. So this equation says that the connected components of this space are exactly morphisms in the homotopy category. But what is nice is that then one can take pi I of this thing. One can look at morphism from the circle to, or one can look at, I don't know, other things like the cohomology of this space. Maybe it's an interesting invariant and so on. So it's a little bit more than just having sets of morphisms. One has actually space of morphisms or homotopy types of morphisms. Okay, and so just a few words to explain where comes from where comes this additional, enriched structure, these two additional enriched structure. So, well, it's a remark. It's not really necessary for what I will say after. So, there is this homotopy category of stacks, and there is this, and this is a model category for the one who knows. And as she said, the model category structure is enough to reconstruct all these invariants, and they are actually really invariants of the model category. So once you are given the model category, everything is going fine. There is a universal property for the homotopy fiber product. These things can be made functorial, so they can be lifted to really actual simple sets and so on. There is a notion of homotopy limits, and so it solves a lot of problems. Now there is something in between, actually. What I like to denote it like this. And this is, well, it's a certain kind of infinite category. And it is exactly the correct structure one should look at. That's the, if you want, the true homotopy category of stacks. And there are several ways to define that. One way is to make the same definition than the homotopy category. So you invert formally the local equivalences, but you invert them not in the world of categories, but in the world of infinite categories. So you ask for a universal property in the world of infinite categories. And so this is also that, but
still you're starting with just usual free sheets, not two free sheets, but three free sheets.
yeah, usual free sheets.
Do you lose anything by doing that?
No.
You get the same thing that if you define infinite free sheets and all that.
So you mean infinite free sheets, you mean lax functors and this kind of thing?
Yeah, like double restriction.
It doesn't, yeah, you get the same category. You get the same infinite category, the infinite categories are equivalent. So this is the specification principle I was talking about. And this category is actually this one up to, you just neglect all the higher morphisms. You make the same construction I was talking about. You take one morphisms and make homotopies between them and mod out by that. And this is a bad thing because one loses every kind of structure here, because then, for example, let me say that this category has all kinds of limits and colimits. Of course, in the sense of, in the infinite category sense, in the higher category sense. So it solves the universal property for the homotopy fiber product. And also, it has it's naturally enriched over the simple sets. So these simple sets are actually the track of the fact that this comes from an infinite category. These simple sets here. So all this enriched structure here becomes property of this category, and one doesn't need any additional structure. This is just a category, and everything is hidden in it.
Could you explain what an S is?
Well, for example, one way to define it is to use the Dwyer-Artin localization. There is I won't explain, no. This is something in, it's funny, I think 79. It's also amazing that such a thing exists since a very long time and people doesn't use it. Dwyer-Artin. It's a simple localization of categories. And then this appears as a simply enriched category, and simply enriched category are actually certain kind of infinite categories. There is a way to see that as higher categories. Okay. Now let's go to examples, I think. Okay, so I'm not going to use this thing, but I just wanted to say that the correct thing to do is to work with that. It also solves the problem that this is not a stack. When you move the base space, for example, you don't obtain a stack when you take the homotopy category. I think people know that the derived category is not a stack. This one is a stack.
So you can actually define the good derived category.
Yeah, exactly the same way. And what is nice is that several model category structure can give the same infinite categories. It's really less than model categories. Model categories sometimes are too strict. So. Okay, so now examples and non-abelian cohomology. So I will give as many as examples I can in 10 minutes. First, a definition for f and f prime through stacks. The space of non-abelian cohomology, of cohomology, of f with coefficient in f prime is by definition this space of morphism. So it's a simple set, or it's a topological spaces. It's only defined up to weak equivalences, but we are going to look at homotopy groups, for example, of this thing, which is well defined, or cohomology, or connected components. There are many invariants that one can define from this. Okay, so example 1. Let's take a space in the base site, and we view it as a fibered category, so as a stacks over X, and so as an object in the homotopy category of stacks. Then we take, so this is going to be F. We take F prime, or not, I don't need F prime. We consider something called KZN. This is a stupid simple sheaf which maps any space to the constant simple sheaf KZN. And this, I remind, this is just a space which is connected and doesn't have any non-trivial homotopy groups except in degree n, which has Z. So it's just something with I equals Z if I got n, and 0 if not. So it's the constant simple sheaf with value in that. And so the first example is that if I take the homotopy groups of the space of morphism, so of the space of cohomology from X to this KZN, I find H the cohomology shifted by I of X. This is sheaf cohomology. And this actually generalizes to the case of a non-constant sheaf. One can take a big sheaf. So if A is a big sheaf of abelian groups on T, then there is the K AN, but then it's not constant anymore. The value depends on Y. So it maps Y to K Y N. So you take the global section over Y, and it's an abelian group, and you make the same construction. So pi i's are 0, but pi n is A of Y. And then
there is because of Z as a free sheaf, right? Not as a sheaf.
Yeah, one doesn't need a sheaf actually. The sheafification is hidden in this passage from simple sheaf to the homotopy category. That's really the principle, that one doesn't talk about descent. So it can be a pre-sheaf also. So one finds H, so the same thing, with coefficient in the big sheaf or the restriction of the small sheaf.
So when you start from a free sheaf, then you get.
This means the cohomology of the associated sheaf. Okay. And this also works when you don't take X to be a space, but you take X to be a topological stack. So as defined by Angelo, or also Kai, then the same equation actually is correct. So a topological stack is a one stack, and as I was explaining, a one stack can be seen as an actual stack by this embedding. So here I use this thing, of course. And this is the Schiff cohomology as defined by Kai Behrendt. In his talk. Okay, no, second example. So this first example is abelian cohomology. There is nothing non-abelian here. Let me give an easy example of non-abelian cohomology. Now one take G a sheaf of groups. On T, and maybe non-abelian groups. Then there is a KG1. It's the same definition as KAN, but with n equal to 1. So there are no homotopy groups except that pi 1 is J. And this exists because the fundamental group can be a non-abelian group. Okay.
What is the difference in PG?
Which PG? Depends of which construction you are talking about. This is how I can define what it is. It is a simple sheaf from topological spaces to simple set, and it maps Y to the usual classifying space of the group of section over Y. So it's a family of PGs. And then there is okay, pi naught. So I will keep the topological space X. Is the same thing as non-abelian cohomology of X with coefficient in G. So this is nothing else than the isomorphism classes of G torsor over X. And there is actually a much, well, slightly more general result. Instead of taking connected components, one can actually take the fundamental groupoid of this simple set. So the fundamental groupoid of this is equivalent as a groupoid to the groupoid of G torsors. So that's a way to reconstruct the whole groupoid of G torsors using this thing. Well, if you look at pi 1, pi 1 is pointed at a point. A point is a G torsor. Pi 1 is the automorphism group of the G torsor you are looking at. When you have a groupoid, the space corresponding to pi 1 is 0. Yeah. There are nothing. Okay, and now what to finish with, I would like to say that these two examples actually are essentially the only one which exists. That means that there are many other examples, but they all are mixtures of these two things. So that's the Postnikov decomposition principle. Postnikov Toën. Well, it's not very general, but it's general enough. You take a stack, and you suppose it has a global point. So suppose that you have something like this, HO of T. You suppose also that it is connected. That means each fiber is connected. Pi naught. That's the point. And you suppose it's n truncated at some point. So there exists an n such that it doesn't have higher homotopy groups. The fibers are n truncated. So this is a pointed, connected n stack, if you want. Then there is a tower of morphisms. like this, with homotopy fibered square, so things like this. Let me put AI. So this is not really well defined once again in the homotopy category, but it means that if one lifts this thing to the category of simple Pleshev and I take the homotopy fiber product, then one gets something which is equivalent to KAI of I, where AI is a sheaf of group. And the construction is given here, so that's this construction. So when you take the space of cohomology, this thing gives you a tower of, it gives you a bunch of vibration sequences. So from F, say Fi, this goes it gives you a homotopy fiber product in a square in the homotopy in the category of simple set, if you want. It means that this is a morphism and this is equivalent to the homotopy fiber of this morphism. So now if you know that this actually computes, it depends of I. If I is 1, this computes non-abelian cohomology in degree 1. That's example 2. So Y is example 2. And if I is bigger than 1, this thing here is given by example 1, which is just abelian cohomology. So what you see is that the space of cohomology of X with coefficient in Fi by induction, you can go to I equal to N, is a successive extension of something like this. So the elementary pieces are just that. So everything has a deduce with abelian cohomology and non-abelian cohomology in degree 1. And that's the Whitehead principle. And we stop with that. So everything is controlled by non-abelian H1 and abelian cohomology. And that's a very important principle we'll be going to use with Tony and myself, I think, in the next lectures. Okay, done.
Any questions? I have a question about the strictification that you use relating one stack to this. So I guess in general, if you've got an in category, you can strictify it at level 1.
No, I'm not strictifying the N category.
You're allowed to strictify them. Is the fact that since, I don't know, the site is a 1 category, then we're allowed to strictify a certain amount and things still work?
The general strictification says the following. It's not a strictification of an N category. It's a strictification of a Lax functor. So essentially it says that you have this N plus 1 category of N categories. This one can be strictified in degree 1. And so I say that any Lax functor like this from a 1 category is actually equivalent to a strict functor. That's what it means.
Sounds like a figure, yeah.